Namaskar and welcome to Study IQ. I am your friend Rahul Saigamkar. Let's continue our discussion for NCERT Science series. We are discussing NCERT Science textbook for class 10, where we are discussing each chapter. Today's agenda is to discuss chapter 13, magnetic effects of electric current. This would be the last interaction where we will be getting knowledge connected to physics. In this NCERT Science textbook, from chapter 1 to chapter 5, we gained insights into topics connected to chemistry. From 6 to 9, we discussed topics connected to biology. And from 10 to 13, today's discussion is about chapter 13. This is connected to topics of physics. Going forward, we'll talk about some environmental issues or environmental topics. All right. So today's agenda is magnetic effects of electric current. I hope you do remember our latest discussion, that is chapter 12, electricity. Why? Because we need to have some inputs from this to understand chapter 13. The title itself is magnetic effects of electric current. We discussed electric current is the movement of electric charge across a particular area for a particular time. So if you have not seen chapter 12, do see it. Chapter 13 would be much more clearer. All right. Right. Let's begin chapter 13. But before that, there is a small notice for all the UPSC civil services aspirants. Study IQ is offering prelims to interview initiative. The August batch is beginning from August 11th. It's a morning batch, 8 a.m. the classes will start. We are providing this program P2I in 3 formats: English, Hindi, and a bilingual format. This is the most comprehensive program where we will be with you through all the phases, through prelims, mains, and interview. The entire program is very comprehensive. It is completely integrated. After every module, there would be MCQ practice. After every module, there would be answer writing practice. The entire program is designed at a very affordable price. And to get maximum discount, do use my code Rahul Live. You'll get max discount. You at the checkout, use this code and get the final price. All right. Right. I'll see you in the class. Right. Let's begin chapter 13, magnetic effects of electric current. As I told you in our previous discussion, we understood the concept of electricity. Now we understood what is electric current. Electric current is because of some sort of difference. We understood it through the analogy of water current, air current. I told you air moves from one place, air as wind moves from one place to another place because of pressure gradient, because of pressure difference. Water because of some gradient, maybe because of gravity, maybe because of some characteristics of water. Similarly, electric current, when it moves, it needs some sort of difference, potential difference. The electric potential difference is needed. So we understood Ohm's law, we understood what is the meaning of resistance, what is resistivity, what does resistance depend upon. And finally, we also discussed about the heating effects of electric current. Now you must be thinking, sir, in the previous discussion, you spoke about heating effects of electric current. That was very fine. We saw some of the practical applications as well in our day-to-day lives. But why there is a separate chapter that has been dedicated for magnetic effects of electric current? Because this has more and more applications in our day-to-day lives. Right now, I'm quite sure you are watching this video and is your fan switched on? Yes. Today morning, did you switch on your water pump? The electric motor which helps to put the water basically from your borewell to the overhead tank. Did you switch on that electric pump, that motor? All those ideas, all those concepts, the fan, that, or any other thing, or any other, your mixer grinder, so many appliances that we have, they work on these concepts. So that is what we are going to understand in this chapter. All right. Now we have gained some knowledge before as well of magnetic field. Now magnetic field, it was basically discovered by a scientist named Hans Christian Ørsted. He accidentally discovered it. He accidentally discovered that electric current, it leads to some magnetic effect, some influence on the magnetic field. What he saw was a wire in which the electric current was passing. It had an impact on the compass, and compass basically points towards north and south. That is the magnetic field, or the magnetic north and magnetic south of the earth. But as soon as the wire, it had an electric current pass through it, it impacted the compass, and because of that, accidentally he discovered that electric current also has some magnetic effects. And that's why the entire idea of magnetic field or magnetic field strength, it is named after Oersted. The unit of magnetic field strength, it is named after this particular scientist. Now, in our previous interactions, when we discussed about the chapters from class 6, 7, 8, 9, we have understood some ideas about magnet and magnetism, right? We have discussed what are bar magnets, right? What are magnetic field lines as well. We discussed about lodestones. We discussed about different magnetic materials, right? The paramagnetic materials, the diamagnetic materials, etc., right? And we saw that for a bar magnet, it will always point towards north and south. We have seen that. And the magnetic field lines, they emerge from the north side or the north pole, and they fall into the south pole. This we have discussed before. All right, means the magnetic field has a particular direction. It has some quantity, it has some magnitude, it also has some direction. Correct? We have discussed this. Meaning, those magnetic lines which are able to reach from north to south, this is done. But the field, it spreads as well. The more the strength of this magnet, the more is the magnetic field around it, and more magnetic field lines around it. And we have also discussed that every magnetic field line, it would always go in only one direction. You know this idea, right? That means it starts from north and it moves towards the south. There would be no magnetic line which would see an opposite end, which would see an opposite side of that. Right? That is established point for us. Now, why am I discussing this? Because this background is needed for us to understand how electric current, it generates magnetic field, or how it impacts, how it has some magnetic effects on other things. Now, let's talk about first thing, how a magnetic field is generated due to a current carrying conductor. Imagine there is a wire, there's a copper wire is a conductor, and it carries electric current through it. Now, what kind of magnetic field it generates? I told you this was accidentally discovered by Oersted. Now, what kind of magnetic field it generates? Now, if it is a simple wire, then that wire will generate a circular magnetic field like this. You can simply run an experiment as well. If you run an experiment, a copper wire through which electric current is passed, you will see the magnetic material, it would align something like this according to the magnetic field. Right? Now, this magnetic field and its direction can be decided or can be gauged through a rule. It is called as the thumb rule, the right hand thumb rule, basically the right hand thumb rule, meaning in whichever direction the current is flowing, hold your thumb towards that direction and rotate your fist. That would give you the direction of the magnetic field that is generated. If the current is in the upward direction, then the magnetic field would be something like this. And if the current is in the downward direction, then the magnetic field direction would be like this. If the current is in this direction, then the field is in the other direction. It is based on your fist, right? All right. Now you must be confused, sir. Will such question come in UPSC examination? Probably not, but we will go eventually to the topic which we want to understand, and for that we need to have this knowledge. So right hand thumb rule, it basically gives you the electric field direction for a current carrying conductor. All right. Now imagine I create a loop of this particular wire. Now what would be the magnetic field? Because of a circular loop, simply use the common sense. There was a straight conductor before. What I have done is I have turned this conductor like this. I have created a loop, and if the electric current was passing in this direction, if I have created a loop, you do understand now that the direction of current is also reversed. So what would happen? If I use the right hand thumb rule? If the current direction is towards, say, north, upwards, then this would be the direction of your magnetic field. But when you come here, the direction of magnetic field is now reversed. So what you will find is you will find loops of magnetic fields along with magnetic field line in directions like this. All right, this is for a current passing through a circular loop. All right, now what do? I create more and more loops. I create more and more loops. I create more and more loops. I take a wire, I create more loops like this, and then I pass electric current through it. A conductor which has been wound, many loops have been created, and I pass electric current through it. Now this is called a solenoid. A solenoid. Solenoid is a conductor which has been formed into multiple loop shape, and I have given it, or I'm passing electric current through it. Now this solenoid, it technically acts like a magnet itself. How? If I put a metal bar inside like this, let me draw that with a different color. Imagine I use a metal bar. Let me take black color and I put a metal bar in this. One second. Right. If I take a metal bar and put here, what would happen? That metal bar would be magnetized. Imagine if that is an iron bar, that would be magnetized. This is the concept of developing electromagnetism, meaning I create, if I have a metallic structure, if I have a simple nail, I take a nail on which I wound a copper wire and I pass electric current through it. That nail itself, it is going to become a magnet, and that magnet will have a north pole and south pole. Why? Because a circular looped wire like this, it is going to have an electric field, a magnetic field very similar to a bar magnet having a north pole and a south pole. Now you're thinking, you're scratching your head, sir, what are you talking about? You're simply telling me some sort of direction, or some rules, right hand thumb rule, left hand thumb rule. What is this? I'll just recap it once again. See, I told you if there is a current carrying wire, it generates a magnetic field, circular magnetic field. Then I simply created a loop out of it. Then I told you if I create multiple loops like this and if I put a bar in it, then it is going to act as electromagnet itself. All right. So a solenoid will lead to creation of a field which is uniform, and I can also create a strong field if I have more and more windings or more and more coils. Now the question is, sir, why did we discuss so many things? Why did we discuss so many things? Because I want to understand something. I want to understand that when I pass electric current through a conductor, through a wire, it generates some sort of magnetic field. And if I have another magnet which generates its own magnetic field, how would it impact the object that is carrying current? I want to understand that. Now what happens is, if I have a magnet, this is a natural horseshoe magnet with a north pole and a south pole, and over it, what I have done, I have used a conductor, and through this conductor I am passing electric current. Now when I pass electric current, this conductor is going to generate its own magnetic field, correct? Now this bar magnet has its own magnetic field, they will interact, and because of this there is movement in this bar. This is what I want to understand, because it has a lot of practical application. Now this is going to move, meaning if I move electric current, or if I pass electric current in one direction, this bar is going to move to one side. If I reverse the current, it is going to move to the other side. I can see the same result if I move this horseshoe magnet as well. Means I understand that some sort of force is applied when I use a conductor through which electric current is passed, which is already in another magnetic field. Now what kind of force and how do I gauge that force? Now that can be understood by the left hand thumb rule, Fleming's left hand thumb rule. Now Fleming's left hand thumb rule will tell you that if there is a magnet, if there is already a magnet, this is a north pole, south pole, that means the magnetic field or the magnetic field or lines of force are in this direction, and you are using a conductor. You are using a conductor in which the direction of current is something like this. Then the motion or the force, the motion of the conductor or the force on that conductor would be in the upward direction. Now that is the Fleming's left hand rule, right? Meaning you use, this is the magnetic This is the magnetic field line. This is the current line. This is the magnetic field line, current line, then the motion towards this side. Now, why I am understanding so many things? Why I am going through so much of technical stuff? Because I have to bring some day-to-day application of this. Based on these concepts, based on these ideas itself, I have created your electric motor. I have created your electric generator. Believe me, we are going to discuss this electric generator in our next class also, which is a discussion about environment, or I would say topic connected to environment, topic connected to energy. So we have created electric motors, electric generators, loudspeakers, etc. Now there is a small question also here. Now this asks you, if an electron enters a magnetic field at right angles, the direction of force acting on the electron will be. Now if you use your Fleming's left hand rule, let's try to get the answer to this. This is the line of the force, this is the direction of the current, okay, and this would be the motion. Now I already have the magnetic field line. This is the magnetic field line. Now you think, is this the movement of the current? No, this is not the current direction. If the electron is moving in this direction, then the current would be in the opposite direction. So this is the field, this is the current. That means the force is acting inwards. All right, so that's how you get your answer. This is basically into the page. The force is into the page. Now, why we are going through this so many technicalities? Because I want to build something like this, say electric motor. Now I want to understand that if I take a magnet and if I place a coil like this and connect it to some sort of an axle, because now I want this axle to rotate. Now what do? I pass electric current. I pass electric current through this circuit. In this direction there is one kind of electric field, and in this direction there is another direction electric field, but this is constant. This electric, I am using the term electric field, pardon me, magnetic field. So this is going to create one magnetic field, this is going to create another magnetic field. These will interact and this will ultimately rotate, and once that rotates, my axle will also rotate. All right, or I can use different kind of split rings and brushes, because of which I can basically translate this into the movement of the axle itself, and that is nothing but your electric motor. I told you, if your fan is on, if your mixer grinder is running, if your pump is running. When I say pump, I'm not talking about the pump which is taking water, but the shaft connected to it, it is nothing but your electric motor. And commercial motors, they do not use magnet. Now you think, sir, do all these motors have magnets, natural magnets? No, they create electromagnets, or they use electromagnets only. See, the electromagnet is used in place of permanent magnet, and for this core, this also has to have some sort of winding. So this electric motor, first of all, this will act as electromagnet, it will have winding, this will also have some sort of winding, and once I pass the electric current through this, because of the interaction of magnetic field, this axle continuously rotates, something like this. And if I connect this shaft to the pump, I can use it as a water pump. If I connect this shaft, say, to fan blades, if I connect this to the fan blades, then it will become your fan. If I connect this to your grinder connection, simply the grinder connection, that connection would be with the grinding jar, it will help you grind. So we have so many applications of electric motor everywhere, and it works basically on the principle of magnetic effects of electric current only. Now you must be thinking, sir, what happens if one of this wire breaks? Or many a times you must have seen the fan won't work, and the electrician would come and he'll tell you, sir, the winding is gone. Yes, the winding is gone, because you can see it is insulated. It acts as a coil. That's why I told you the concept of solenoid was such that you have winding over this. Now this becomes electromagnet. There is no need to send the current directly into the metal or into the conductor at all. So this basically acts as a coil which magnetizes this, and another coil which magnetizes this, because of which it rotates. Clear? Right. So this is one of the applications. Another application, we use loudspeakers, right? Loudspeaker also has the same concept, and loudspeaker, they literally use the magnet itself. Have you seen it? Have you seen it? If it is a very huge kind of a speaker, they might use electromagnets, but many speakers, they have natural magnet itself. Now we used to do this when we were kids. If some speaker has spoiled, then we used to take out the magnet out of it, because magnet, again, it's fun to play with, right? Have you done that? Because on that magnet you would have some kind of a cone, and you will see, because of the magnet and because of the coil on it, this magnet is going to generate a magnetic field. When I pass electric current through this coil, this is going to generate another magnetic field. Because of this interaction, ultimately the object is moving, and once the object moves, the diaphragm moves, it is going to create sound waves. That's how loudspeaker works. Same way your microphones work. Same way your microphone works. Say, very similar way your earphones also work. A very small such circuit is present there. All right, right. So I hope things are clear connected to magnetic effects of electric current. One thing that we understood, because of this magnetic effect, I can make an object move. I can make an object move. Correct? We have understood this. Now, is the reverse phenomena possible? What we have studied till now is a current carrying conductor. When it is placed in a magnetic field, it can move. I have ensured that either it rotates, especially in electric motor, or I gave you another example of loudspeaker as well. It moves in this direction. Now the question is, there is a reverse possible. Now what is the reverse of this? The reverse of this is, if I have a conductor which is, say, again, a current carrying conductor, if I am able to move it, can it generate electricity? Can it generate electric current? Is it possible? Meaning, one electromagnet which has some magnetic field, if I move it, can it lead to creation of electric current somewhere else? That is possible. It was discovered by Michael Faraday, and that is what we basically do when we talk about your generators. What is your generator? See, a motion which ultimately produces some sort of electric current or EMF. Meaning, there is a rotating shaft. And this shaft has some coil. Now, although this is a magnet, imagine this is a coil, basically electromagnet itself, which has its magnetic field. And when this is rotating, this magnetic field interacts with another coil, its magnetic field, and produces EMF. Is it possible? Of course, yes. That is how we generate our electricity. That is the same concept, or that is the same concept in our electric generator itself. The electric generator, we'll talk about it. Now, for the electric generator, now the rules differ. We saw for the electric motor, we saw the left hand Fleming rule, and for generation, we use right hand Fleming's rule. Meaning, there is a magnetic field which is in this particular direction, and the movement of the conductor is in this direction. This is the field, this is the conductor movement. Then the EMF or the electric current is induced in this direction. That would be gauged through the right hand Fleming's rule. And using this right hand Fleming rule, using this concept itself, we create electric generators. Now, what is this generator? What is the generator? Now, this generator, first of all, it will have a magnet. So this has its own magnetic field. Now, what I am telling you is, when I rotate this, then the coil that is moving here, it will generate some sort of EMF or electric current, which I can measure using the ammeter. That is what we do in electric generators. Have you seen the movie Swades? Yes, you've seen the movie Swades. What Shah Rukh Khan does is, he has created a small reservoir in that village. Water is collected in it. He opens the valve. As soon as he opens the valve, then the water hits the turbine. Turbine has turbine blades. Now, that turbine is something which is rotating. Now, that rotating turbine shaft which is there, this is connected to coil 1. And as soon as it reaches a particular speed, this becomes electromagnet 1. There is another coil. In general, in a generator, what do we have? There is a structure called as stator. This is called as stator. The stator has separate coils on it, and this basically becomes your rotor. because this is rotating. Now this rotor is going to generate current into your stator circuit, and this stator circuit you would send it to the substation where you can pass the electricity forward. That's the basic idea of generation, electricity generation, where you use this motion, and that motion can be induced by anything. That motion can be induced by water, it becomes a hydroelectric generator. That motion can be induced by steam. Normally we use steam on the turbine. The turbine rotates, and then that means the rotor is rotating, the rotor coil is active. Now the rotor coil will generate the current in the stator coil that would be used, or that would be transmitted forward. That's the basic idea of electric generators. Please remember this, because we will be talking about this in our subsequent discussion as well. Now, apart from this, one last topic which is there is our domestic electric circuits. Now, in our domestic electric circuits, you must have seen how electricity reaches us. It reaches at particular voltage. At home, we have a 220 volt setup with a potential difference of 220. Then we have a circuitry something like this, where you have a live wire through which the current passes. You have a neutral wire. You also have a fuse, because if the voltage becomes high, then if the voltage is high, then the current would also be extremely high, and when this current passes through it, the fuse will burn off because of the heating effect. There is also an earth wire which is used, the third wire, the earth wire is used. This is used so that earthing happens, you do not get that electric shock. And generally, I told you, we connect from our main distribution board, we use parallel connection to different equipments. Generally at our house, we do have, again, whenever we need more current, say there are many equipments which need 15 ampere current, there are some equipments which need 5 ampere current, there are some which needs less current than this as well. So we create different kinds of parallel circuits so that requisite current can reach there. All right. Generally the normal bulbs that we have, bulbs, fans, or whatever low load or low wattage equipments that we use, they use 5 ampere current. And if we have an AC or a cooler, or your pump, your electric motor, which is about 1 HP or say 2 HP, that requires higher wattage, that means that those require about 15 amperes power. So we give separate parallel connections to those. That's the basic domestic circuit that we have. All right. So I hope things are clear for you from the examination perspective. What is the domestic circuit? What are the magnetic effects of electric current? Clear? Right. So that's the end of today's interaction. Again, if you like this interaction, if you have any queries, if you have any suggestions, you can always reach out to me on this particular ID, Rahul Sai 222. Thank you again. Jai Hind.